In this video, I'll be going over the basics of sigma notation. So we'll start with a question. Suppose we want to find the sum of the first 20 positive integers. So what this means is we want to find the sum of 1 plus 2 plus 3 plus all the way up to plus 19 plus 20. So we could do this, manually. There's a couple tricks we could do to find this sum fairly quickly, but it's a little bit cumbersome to go through and find this sum. Imagine if we wanted to find the sum of the first 100 positive integers. Again, we could do this if we had enough time and patience, but it's a little bit tedious. So sigma notation allows us to find the sum of a sequence like this, and it allows us to write that sum in a shorthand way. So if we wanted to rewrite this using sigma notation, we write this Greek letter, which is capital sigma, and we're going to say I is equal to 1, and we're going up to 20 of I like this. So let's talk about what this means. So this is saying we're sigma, that tells us we want to find the sum of these terms. Okay, now what are those terms? Well, we're starting with I, and down here this is telling us the starting value for I, and then we're going to end at this value. Okay, so whatever value is down below the sigma, whatever I is equal to, that's telling us what we make I equal to in our first term. And then we just count by integers from whatever our first I value is. So it's going to be, this is going to be equal to this sigma, this expression using sigma notation is going to be 1 because that's our first I value, plus 2, plus 3, plus all the way up to 20. Okay, so this is a quick way we could write the sum of the first 20 positive integers. We haven't talked yet about how to actually find this sum, but the first thing we want to do is write this in sigma notation. Now suppose we want to write or want to find the sum of the first 100 positive integers. Well, again, we're going to use sigma notation anytime we're talking about a sum of a sequence. We can use sigma notation. So if we want the first 100 integers, again, the first positive, or I should say the first 100 positive integers, we're going to start at the first positive integer, so I is equal to 1. We're going to end at 100, and then this is going to be I here as, it's kind of like our function. It's not really a function, but we can think of it somewhat like that. All right, so again, this would be equal to 1 plus 2 plus ... all the way up to 99 plus 100. All right, so now let's make it a little bit more general. We want to find the sum of the first n integers, and let's say n positive integers. All right, so the first positive integer is 1, plus 2, plus 3, plus... Now we don't know how far up we're going to go. We're going to go up to whatever our n value is. So if n is 20, we're going to go up to 20. If n is 100, we're going to go up to 100. But we don't know what n is, so we're going to end at n, and then the number right before n is n minus 1. And then the number right before that is n minus 2, and so on. Okay, so this is what we would want. Or if we were going to write this out position by position, this is how we could do it. And then to write this in sigma notation, well, we're going to start at 1, and then we're going to go up to n, and I will be right here. Now oftentimes we'll replace this I with a sub I. Now a sub I, this is, now the I is going to be take the place of this subscript. So it's kind of like A1 plus A2 plus A3 plus dot 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 and so on. So in this instance, this is just a way of saying which term. So this right here is the first term and so on. Here's the second term and so on. So if it was A sub n, that would be the nth term of our series. So let's expand a couple of expressions written in sigma notation. So if I had a sequence starting at 2, going up to 7, and we have s sub I, well, what this means is our first I value is going to be 2. So we're going to say s sub 2 plus s sub 3 all the way up to s sub 7. Now we don't know here what s is, but this is saying add the second value, or the second term plus the third term, fourth term, and so on. Another one here, I wrote sigma x, sigma, of I equals 0 to 4 of I over I plus 1. Okay, so when we have I, we're just going to input whatever the first value of I is, which is 0. And we're going to do that until we end up with I equals 4. So I equals 0, we get that fraction, then 1 over 1 plus 1, plus 2 over 2 plus 1, plus 3 over 3 plus 1, plus 4 over 4 plus 1. Okay, so we could simplify this. I trust that you could do that. If we simplified, added these up, we would get 163 over 60. So here's our sum, 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25. And we want to write this in sigma notation. So it looks like what's happening, or the pattern we have, is we have fractions with 1 over some integer. And those integers are all perfect squares. So this is 2 squared, 3 squared, 4 squared, 5 squared. We could rewrite this first term as 1 over 1 squared. So it looks like what's happening is the denominator is just increasing by 1 each time, and we're squaring that denominator. And it looks like we're going from 1 to 5. So writing this in sigma notation, I'm going to say I is equal to 1. We're going up to 5. And all of these are fractions with 1 in the numerator. And then the denominator is, we're starting at 1, and then we're squaring that. So 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on, up to 1 over 5 squared. Here are some of the basic properties of sigma notation. So I'll go through each of these. This first one says, before I do that, let me just say that we're going to let C equal a constant here. Okay, so property A says if we are summing from 1 to n of any constant, all that we do is we multiply n times that constant. Now to explain this, suppose we have I equals 1, and we're summing that 5 to the 5th term, or we're summing this 5 times, and our constant here is 2. What that means is we're going to say 2 plus 2 plus 2 plus 2 plus 2. So that is 5 terms. So another way of thinking about this is just 5 times 2. So that's what this n times c means. The second property, property B, says if we have a constant here getting multiplied by each term, what we can do is we can take that constant out of the sigma notation, kind of like when we had an integral with a constant or a limit with a constant. We can take that out. We can think of it kind of like factoring that out of the expression. Property C, this is just a sum and difference property for sigma notation. So if we are summing two terms that are either getting added or subtracted, we can separate those as two separate expressions in sigma notation. And then D, E, and F, these are just some of the common sigma notation expressions that we'll end up with, either I or I squared or I cubed. Oftentimes we will have a more complicated expression that we are summing, but if we can simplify it down to I squared, or I cubed, we can use one of these expressions to find the sum. All right. Our first example says to find the sum of, or find the value of sigma from 1 to 100 of 3 minus 2i, and we're actually going to square this. So before we try to address finding the sum here, let's just expand a little bit of what we're talking about. So if I is, and before I even do that, let's see, how do I want to do this? Do I want to expand first, or let's not expand first? So what this means is our first term, we're going to say 3 minus 2 times 1. That's getting squared, so I is just taking, or 1 is taking the place of I. Then we're going to add that to 3 minus 2 times 2 squared times 3 plus, 3 minus 2 times 3 quantity squared plus, and so on and so forth. And then we're going to, the last two terms will be 3 minus 2 times 99 squared plus 3 minus 2 times 100 quantity squared. So that's the expression we're going to find the sum of. So there's going to be 100 terms here. Now, again, it'd be kind of ridiculous to actually write all of this out and find the sum. You could do this if you had enough time and paper and patience, but again, be easy to make a mistake and pretty tedious. So instead of doing that, we're going to use the properties of sigma notation that we were just looking at. So the first thing I'm going to do is I'm going to expand this expression. So this is 3 minus 2i times 3 minus 2i. So multiplying that out, I'm going to get 9 minus 6i minus 6i. So minus 12i, and then plus negative 2i times negative 2i is plus 4i squared. And we want to keep that in parentheses because we want to show that we're taking the sum of that entire expression. Okay, so what we saw back here with this sum and difference property was that if we have the sum or difference that we're taking we're applying that sigma to, we can split that up into multiple terms. So that's what we're going to start with here. So I'm going to rewrite this. I is equal to 1 to 100 of 9 minus sigma from 1 to 100 of negative or minus 12i, and then plus I is equal to 1 to 100 of 4i squared. Okay, so it's kind of like we're distributing this through. I mean, that's not technically what's happening because we're not multiplying that, but it's getting applied to each term. Okay, so this first term from 1 to 100 of 9, well, that is just going to be this first property up here. Okay, we have a constant and it's getting applied n times. So here, this constant is 9. It's getting applied 100 times. So that's 9 times 100 minus, in this instance, I have a constant getting multiplied by I. So I'm going to write the I, or the 12 out front. And I'm just left with I inside. And then same thing. On the third term, I have a 4. So I'm going to say plus 4 sigma from I equals 1 to 100 of I squared. So this is really a good place for us because we want to get to the point where we have I or I squared or I cubed, because back here we know what to do when we have I, and we know what we do, or what to do when we have I squared. Okay, so we're going to apply both of these in this last step. And I'm going to do this off to the side, just so I have enough room, from 1 to 100. Okay, so how we tackle this is, well, this is going to be n times n plus 1 divided by 2. So our n value is 100 here. N is 100, so we're going to rewrite this as 100 times 100 plus 1 divided by 2. So that's 100 times 101 divided by 2. Okay, so that's what's going to take the place of this guy right here. Okay, so this will be minus 12 times 100 times 101 divided by 2. Okay, and then the third term, I'm just going to talk about what this is equal to. Well, when we have I squared, that's equal to n times n plus 1 times 2n plus 1 divided by 6. So using what we're given, or applying this to what we were given, we're going to have 100, because that's our n value, n plus 1, so that's 101, and then 2n plus 1, so that's 2 times 100 is 200 plus 1, and then divided by 6. Okay, and then all of this is going to take the place of this guy, so this will be plus 4 times 100 times 101 times 201 divided by 6. Okay, and then we can bring down this first term. 9 times 100 is 900. Okay, so I trust that you can calculate this from here. If you want to pause the video and calculate it on your own, and then you can check your work. But when I do this, I get 1,293,700 as the sum. And let's look at one last example. So let's find the value of sigma from 1 to 6 of I cubed minus I squared. So the first thing I'm going to do is write a good sigma symbol. So I is equal to 1 to 6, from 1 to 6. So I'm going to split this up into a difference, like this. Okay, and then I cubed. Remember, I cubed is of I cubed. This is n times n plus 1 divided by 2, and that is getting squared. So applying that to this first term, our n value is 6, so this will be 6 times 6 plus 1 is 7 divided by 2, and that's getting squared, minus, well, when we have I squared, that is equal to n times n plus 1 times n plus 2 divided by 6. So again, on the second term, our n value is 6. So this will be 6 times 6 plus 1 is 7 times 6 plus 2. Oops, I made a mistake here. Let's clean this up. I wrote this part wrong. That's a common mistake. I was not n plus 2. This is 2n plus 1 is what we want to write there. So n times n plus 1 times 2n plus 1. So our n value is 6, so I have 6 times 6 plus 1 is 7 times 2 times 6 is 12 plus 1 is 13 here. And then we divide that by 6. Okay, I'll just put that in square brackets to make it look nice and neat. So that first term we get 1764 divided by 4. The second term we get 546 divided by 6. When we subtract those, we get 350. All right, so if you haven't really worked with sigma notation before, this is hopefully a good introduction for you. And this will give us just enough of what we need in order to really dive into integration.